were in the middle of, or really not so much in the middle of, as opposed to like 2/3 or 4/5 or maybe even 5/6 to the proof of the statement, but we'll go through it again. It's a nice method. It deserves a little attention. Sigma 0, 3. Is sigma 0, 3 complete? And we certainly did complete the first part of this, that it is in fact in sigma 0, 3 by just writing down a formula. And then we said, okay, now that we have this, we have to show that for any A which is in sigma 0, 3, that we can find a one reduction that reduces this A to COF. This is the remaining task we have to deal with. And I already described the global strategy. The global strategy was find a B which is computably enumerable, such that x is in A if and only if B super x is cofinite. Right? And we thought about it for a moment and realized that really, if we can do this, this B will give rise to the one reduction we want, because the question you asked for is x in A, is the question, is the x column of B cofinite? And for different values of x, that's different questions, so you have a 1-1 reduction. So this is our task. Now, I'm going to use a fact that is not that hard to prove, but I'm not going to prove it. Inf is pi 2. The set of indices of infinite CE sets is pi 2 complete. Right? i.e. it is pi 2, and any other pi 2 set 1-1 reduces to this. So we're going to use this fact to construct our B. And how does this go? Well, we know that, well, we assumed A is sigma 0, 3. Well, what does it mean? It means it is of the form there exists a y, rxy, where r is in pi 2. I guess I should again be consistent in whether or not I leave out the super zero. So let me just put it in. But this is what it means to be sigma 0, 3. But now we have this R is pi 2, inf is pi 2 complete, so this R reduces to inf, which tells us that there exists a computable G such that x is an A if and only if there exists a y such that w g of x, y is infinite. Right? And of course, this part of the proof is a little unsatisfying because we did not prove that pi 2 is, that inf is pi 2 complete. But as soon as you are willing to, at least temporarily until you get home and you can check the proof or come up with the proof yourself, if you're willing to assume this fact, then we get such a computable G. And that's not too bad, right? We want our Bx to be cofinite, at least we can get some CE sets which are infinite. So now we want to use these infinite CE sets in order to construct our B, and we already know sort of the main idea for the construction of our B, which is movable marker construction. What was the idea of a movable marker construction? Well, at any stage, you label all the elements of the complement of B. Right? B is finite, so you can imagine doing this labeling. And then depending on certain computable conditions, you move some markers. Okay, so what does this mean? Well, right, construction in stages. Right, now we have two parts of strategy in the construction we're doing together. One is we're constructing a CE set. So the construction should kind of look like do computable stuff and every now and then stick something in B. On the other hand, on top of this, we put this movable marker construction, which is a good way to do the bookkeeping and understand what's going on. Of course, we start with B being 0, and now at some later stage, so at stage s plus 1, what do? Well, at stage s plus 1, we label, we do it column-wise. We look at the xth column of B, and we label all these elements there. So label all the elements in the complement on this next column. What did I write here? Yes. For every y less than or equal to s, if we find that wgxy s is not equal to wgxy s plus 1, then we take marker bys and we put it into bs plus 1. Okay. No, this is the way. Right, so we need to see a couple of things here. Computable stuff, every now and then decide to stick something in B. Right, so is this all computable stuff? Well, yes, it's all computable stuff. We have finitely many y to consider, and for each of these y, we compute some finite approximations to wg of xy. Right? Finite approximations, the comma s versions are always computable, and you just check what is in there. Well, the only things that could be in there are strictly less than s plus 1. So you have finitely many elements to check for. For these finitely many elements, you have finitely long computations to do. So here indeed we have a computable condition to check. So finitely many times we check a computable condition. In case the condition is true, these things are different, you enumerate something in there. So at least that analysis shows that we do end up with B being CE.
Should there be an x somewhere in that bottom piece? Like the x j plus 1 or something? Or are you fixing x in the beginning?
The x is here.
Right, but should there be an x in the line below that?
Oh, I guess it's kind of crappy notation.
The book they just got rid of
I
it,
guess,
so.
yeah, maybe I should do it like this.
Okay.
Right, I enumerated the xth column, and I'm looking at what happens in the xth column. So this labeling
Right,
implicitly had the x in there, I guess.
Really that should be xj plus 1 or something? To the right?
Yes.
Yeah, that's okay. So you're
or
filling it
better
up
yet,
column by column.
maybe even better, because then what does it mean to enumerate into the X column? Well, it means to stick this pair into the right set. And I'm sure that if you didn't realize what the problem was, the changes have been really confusing. But right, what we're looking at is for every X, well, we want to do something here for every X. Now we don't have to do something for every X because, well, if we want to do something for every X, we still only have to look at finitely many cases because everything here is bounded by S. And so computations involving an X which is bigger than S will never converge in less than S steps. So you only have to look for the first S axis, what happens there. For each of those you do this computation, you say, okay, look at the X column of BS, enumerate it like this, check if my W approximation changed. If it did, stick in the corresponding marker. And so, even though the details are now correct, the analysis to see that it's computable stuff followed by enumerating something is still exactly the same. So now all we need to see is that this works. Does it work? I want that if X is in A, the X column of B is cofinite. Right? Almost everything is in the X column of B. Well, there can be finitely many exceptions, but so now we can repeat quickly. Or I don't remember if I did it quickly at the end of last lecture, in which case I should do it slowly now, or whether I did it slow enough at the end of last lecture, in which case I should quickly remind you. So let me take the average and do an intermediate reminder, and if it's too quick, then you can tell me to go slower. Right? If we just focus our attention on the X column of B, because the analysis is per column anyway, so you don't have to worry too much about what happens globally. If we just look at the X column, and we have these markers, so what does it mean to stick this thing into the X column? Well, essentially it means that you slide all markers over by one. Right? If I enumerate B1 into B, then the next time I put my markers down, it just means that B1 is in the next position. And B2 used to be here, but it's one position over. Right? So this is why sticking an element in the X column exactly corresponds to sliding all the markers over by one step. So now what do we want to see? We want to see, well, when is this kind of thing cofinite and when is it not? So when is it cofinite? It is cofinite if the complement of this column, the thing we're talking about here, is finite. How do you get it finite? Well, as soon as there exists one marker which moves infinitely much, right? If there is one marker which infinitely often gets slid upwards, then it and all the markers above it will never have a final resting place on a number, and so don't correspond to actual numbers of the complement. So the X column being cofinite is implied by there exists a marker which moves infinitely much. Now we want to see that it's equivalent, that the X column is cofinite if and only if there is a marker which moves infinitely much. So suppose there is no marker which moves infinitely much. This means that if I take any finite initial segment of the markers, eventually all of the markers in this finite initial segment come to a rest. And that means that the complement of B, the complement of the X column of B, is at least as big as that initial segment. And because I took an arbitrarily long initial segment, there is arbitrarily many finite numbers in the complement of B. Therefore, there's infinitely many numbers in the complement of B. Right? So this argument showed that bx is cofinite if and only if there is a marker which moves infinitely much. Right? You really want to kind of think about it as a dynamic thing. If you keep moving this marker away and away and away and away, then everything falls off at infinity. If all the markers come to a resting place, then infinitely many markers have a finite permanent position, and they denote the complement. Therefore, the complement is infinite. So this is now what we have to see works. And what do we have to work with? Well, if x is in A, then there exists a y such that wg of xy is infinite. Well, if there exists a y such that wg of xy is infinite, if it's infinite, then at infinitely many stages a new element gets enumerated into this wg of xy. And what is our construction? It says exactly, when you notice that there is a new element in wg of xy, you move the corresponding marker once. So the yth marker moves infinitely many times if the wg of xy is infinite. If it's infinite, infinitely often you see a new element, infinitely often the yth marker moves. So these wg of xy being infinite means the corresponding marker moves infinitely much. If, on the other hand, there does not exist a y such that g of xy is infinite, that means all of them are finite. That means that for every y, all of the gx y prime with y prime less than y are finite. So all the markers corresponding to smaller sets move finitely much, and after all of them have stopped moving, g of xy is also finite, which gives it maybe finitely many more jumps to do. But finite plus finite plus finite plus finite plus finite is finite, therefore the yth marker moves only finitely much. Which proves the theorem. Which part needs elucidation? I get this general sense that have been not quite clear enough. Right? So let's review. Let's review and see if it helps. Okay, we have our A, and by just pretending we knew some things, we got this function G. G is computable. It has a special property. If you're in A, the wg of xy is infinite. Right? This was a black box construction. The proof is in the book. I'm not going to do it because I'm too lazy. But as soon as we have this, now our construction of the set, let's just ignore the x column, think about one set. We have this one set, we enumerate its complement with markers, we put these markers in its place, and we make sure that the yth marker moves every time wg of xy gets a new element. Now, of course, if the yth marker moves, the y plus first marker also moves, right? Because the markers push each other over like that. But now we have two cases to consider. Either there is a y such that wg of xy is infinite. Well, this means that the yth marker moves infinitely much. Maybe it moves infinitely much plus a bunch of other times because of the smaller sets, but infinite plus other stuff is still infinite, right? We're dealing only with countable infinities here. So as soon as there is an infinite set, wg of xy is infinite, one of the markers moves infinitely much, therefore the complement is finite. The other case is all of the wg of xy are finite, and then you can argue by induction that, well, if the yth marker at some point comes to a rest, then the y plus first marker no longer moves because the yth marker moves, so it only moves when a new element appears in wg of xy, and that happens only finitely much. So after the yth marker comes to rest, finitely many later stages, the y plus first marker comes to a rest, and that is an inductive proof of all the markers come to a rest. I guess I did not do the base case, but Wg of x0 is also finite, so the zeroth marker will finitely much. I guess there's all of the markers before the zeroth marker also come to a rest. Did it help? It's kind of a nice construction, right? You have these markers. If you don't think it's a nice construction now, you really just need to get a cup of coffee, sit down, relax a little. Right? There is just 3 facts which you need to see, or 3 statements that you need to see that correspond to each other nicely. A funny characterization of A using this G, the construction that exactly says the white marker moves if a new element appeared, and the observation cofinite means there is a marker that moves infinitely much. Each of these 3 facts are kind of separate. And once you have them all, you have to prove it further. Okay. So then we'll move on to the high domination theorem, which has nothing to do with this, but is just a really nice observation. So what is the high domination theorem about? Well, we know what high sets are, and we've also observed in some other situations that it's useful to have nice characterizations for the sets we deal with. And so this is exactly one of the things the high domination theorem provides. It says 0 double jump Turing reduces to a jump, right? A as an oracle is as powerful as 0 jump is as an oracle. Is equivalent to there exists an F Turing reducible from A, which is dominant. So its power as an oracle can be characterized in terms of this one specific type of function which is computable from A. So what does it mean to be dominant? Dominant means dominates every total computable function. Right, and remember, dominate means, right? So for every G, which is a total computable function, we have that G is less than or equal star to F. Now, if you didn't know what dominant means, then this is probably not going to help you. But G less than or equal star F meant for all but finitely many input values, F is greater or equal to G. Or equally, there exists a natural number such that for all larger natural numbers, F is greater than G. And you want to think of this as F is greater than G, but you want to think the right way to say it, again rephrasing, is F is greater than G up to finitely many exceptions. Which is clearly as good as you could get because all the constant functions are total computable, and if you didn't leave the star in, there would be no such F. Should you still believe there should be such an F, or is there a reason to worry. Well, I guess the theorem says there is such an f, but there is an easier way to see that there is an f which is dominant than to see there is an f which is Turing computable by a certain set which is dominant. But how do you in general get dominant functions? Sort of a nice observation which I think illustrates dominance a little bit.
Well, can you argue by contradiction? I mean, if there wasn't, then you'd have some sort of cardinality problem.
Cardinality is the right thing.
Can you enumerate all these? There's only countably many total computables, and then you just like it. You dominate finitely many at each stage, and then you just
Exactly. There's only so cardinality. It's exactly because it's countable. So there is cardinality there. But if you have any collection of countably many functions from the naturals to the naturals, then from this you can get the function, you can even write it down completely explicitly. F of n is equal to the maximum of g I of n for I less than or equal to n. Right? And this is from the nth input on, you're considering the nth function in your enumeration, and then you take the maximum over those. So certainly from the nth input on, you're greater or equal than the nth function. Maybe before already, right? You don't know what the nth function does before, but at least from that point on, you dominate it and you're bigger than it. And so this shows that certainly dominant functions exist because there's only countably many Turing programs, therefore countably many computable functions. Of those countably many, at most countably many are total. You know, in fact, there are exactly countably many total functions because we have an upper bound, and 10 seconds ago I gave you a lower bound, right? All the constant functions. Dominant functions exist. But this theorem, the high domination theorem, exactly characterizes highness in terms of being able to compute a dominant function. Which I think it's pretty cool, quite frankly. Everybody happy with dominant now? Right, and you notice me checking my notes, of course. It's clear that if you think about the proof, you need totality, but you only dominate the total functions. You don't care about the partial ones. This will be a key fact in the proof here. Okay, what does the proof look like? Well, first observe, again, I'm going to use fact. Right? When I say fact, this is something that you should believe me when I say it's true, but I haven't proven it, and I probably won't either. Tot is Turing equivalent to zero double jump. Right? The set of indices of total functions is a set, which is equally complicated as zero double jump. Also, this is not a fact because we've proved it. Zero double jump Turing reduces to a jump if and only if there is an a computable G such that limit S G of E S is equal to top E. Right? This says there exists a computable function of two arguments that, well, it doesn't give you the characteristic function of a set of total indices, but its limit over the second coordinate gives you the characteristic function of total functions. And now you could object a little bit. and say, well, that's not a theorem I remember proving, and that would be correct. But we proved it. We proved this statement for a situation where A was the empty set, and this is again one of these situations where the whole proof relativizes to just taking the oracle A, working relative to the oracle A, everything in the proof where before it says computable, you now write A computable, and the whole proof goes through perfectly fine. Right? This is about limit-wise computable functions, so the limit lemma, if you're trying to find it in the index. The limit lemma is this, but this is now the relativized version. Okay, and it's wonderful because, of course, 1/2 of this equivalence is 1/2 of the equivalence we're trying to prove. So this is clearly a useful characterization. Okay. 2 implications. First, if 0 double jump reduces to A, we should be able to come up with this dominant function. What do we know if we have 0 double jump reducing to A? Well, there exists an A computable function G, which in the limit describes the characteristic function of the total of the set of total indices. So we're going to use that, and using that we can write down, so I'll just plunk it down and then try and figure out why this might be the right equation. So the first thing you notice is that this f, the definition of this f, is not entirely dissimilar from the definition here. We take the maximum over some growing number of things, which is a good way to build a dominating function. We take the maximum of this growing number of things, and what we want from this growing number of things is to what do we want? Well, we want to see that this function is dominant. What is T of E? Right? T of E, we look here, and we notice that T of E is claiming something about the ETH index. What is it claiming? Where did my ask go to? Should be, at the very least, be right. This T E. I think that's better. What is TES? So what is the trick? Well, at stage S, we want to say, okay, at this stage S, we're going to look forward and see if we can determine what the value should be of this function phi e. Now, of course, one case is really easy. If this phi e converges and you just start looking ahead, then at some point you'll see that it converges and you're done. So the big problem is when this function does not converge. You start looking ahead. Right? We start looking from time S onwards, doing more and more computational steps to see if this converges. Every now and then, for some of these x's, you see that now it starts converging. For some other ones, you don't see that they converge. And so there is a holding problem, which a priori you cannot solve. When have when has phi e converged on all the x less than s on which it will converge at all. So you couldn't compute this. But now, of course, we are using, that's why we're using this function g. What is the property of the function g? Well, g on first input e, as you give it second inputs, it gives you guesses about whether the function is total or not. Right? If g(et) is equal to 1, then the current guess of g is that the function is total. If g(et) is 0, then the current guess of the function is that it's not total. Right? And these guesses can fluctuate a ton, but because we have this g and its limit is equal to the actual characteristic function, right? How does your limit become equal to either 0 or 1 in this case? If from some point on your guess is correct. Right? So from some point on, for sufficiently large t, it gives output 0 if it's partial, it gives output 1 if it's total. So now what is this search, right? We're looking for the least t greater than s, such that this happens. What are we searching for? We're looking for the least t, such that either our function g makes a guess that the index e corresponds to a partial function, in which case we don't care. Or, if you never find a t that says, I now guess that it's partial, so if this is always equal to 1, well, if it's always equal to 1, then the limit is really equal to 1. The limit equal to 1 means that this function is total, and so it certainly converges on all of these functions. So this is what the function t does. It starts looking from point s onward, and it says, I'm going to keep on computing until either everything converges, or g tells me that I shouldn't keep searching. And so, if s is sufficiently large, then g for everything bigger than s is always the right value. And so you compute the right thing over here. Everybody happy with t? So t of e, right? E is kind of fixed in nullity. T of e says, look from s onward, either look for a time where everything we want now converges, or where g tells us that we shouldn't keep looking. And because g is a-computable, this function t is also a-computable, right? This here is computable, this is a-computable, so the whole expression is a-computable, and then we close on a minimization. And I just argued, not explicitly, but certainly implicitly, that this function t is total, right? Because g does indeed have this limit behavior. So you either will find a 0, or you will find that everything converges. So this is a total a-computable function. Everybody happy with t? Look far enough ahead, everything converges, or you should just hope that it doesn't matter. Okay. So now what? Now I'll try to. When I wrote my notes, I'm pretty sure I copied from the book, and moreover, I was in total agreement with what I was writing down. Right? That's why I write things over. I don't write class notes because I like copying things from the book. I write them because as you write them, I check them carefully. But you can see that that clearly didn't work out so well here. Because now this fs, right, we want to argue from this definition that for every e, if phi e is total, then phi e is eventually dominated by f. And we would like to argue this in as simple a way as possible. Right? This definition of t and f almost certainly works, but in a slightly circular way, because this t, of course, isn't really the right thing to compare with an output of phi of e. This t says something about how long you should be computing something to get this output of e. It's not the actual output. But now, of course, you could fix this by saying, okay, if I bound myself by these times, then I now change, I can find an e prime, which first checks how long it should take, and then keeps on computing that long, and you still dominate. But that's clearly kind of circular. It's much better to just use this time to start computing, which to me seems we should have here phi of e of t e s of s of e less than or equal to s. Right? Now f of s takes a maximum of output values of phi of e, which should be much easier to argue that you dominate. Right, so now we need to see this. If it's total, it should dominate. If it's not total, we could not care less. Right? So assume we have an e such that phi of e is total. Now we want to see that fs dominates. Okay, so what does it mean for phi of e to be total? It means that the limit of ges as s goes towards infinity is equal to 1. Right? What does that mean? It means that from some point on, let's say time t, from some point on, ge of s is always equal to 1. As long as s is greater than t, you're equal to 1. What does that mean? Well, it means that in the definition of t, you never compute the output because g gives you output 0. You always get the output because all the input values converge. What does that mean? Well, all the input values converge means for every input value less than or equal to s, in particular s itself, you converge in t many steps. And that means that for every s which is greater or equal to this t, this phi e of tes, this value, tes, is great enough to indeed dominate the time it takes for this computation to converge. And therefore, you really consider this particular phi e amongst the things you take the maximum of, and therefore you're greater or equal than that phi e.
So one thing you're taking the max over is actually that value. So
Exactly. Yeah. That's why I fix it up like this. You can fix it up another way, but I think this one's better. The value you're trying to be bigger of is one of the ones you take a maximum of. And so you take a maximum over these phi e, and then you argue that this t really is a time which is big enough, and this time is big enough just as soon as you're bigger than the t, from which point this function always gives output 1, because this never applies anymore. Good. So if a jump computes 0 double jump, we get a dominant function. That's what I just showed. So now we need the other direction. The other direction says we have a function f which is a computable which is dominant, and from the existence of this function f, we want to see that a jump computes 0 double jump. Or equivalently, we want to find from this dominant function an a-computable function that in the limit computes the characteristic function of the total functions. Let's hope that my agreement with what I wrote here as I was writing my notes still holds up. This is equal to 1 if for every z less than or equal to s, phi e of fs of z converges and 0 otherwise. This looks good to me. So this is certainly a-computable, because it uses f, which is a-computable. Everything else here is computable. So this function g is a-computable, and all we need to see is that the limit over s of g e s is indeed 1 if the function e is total, and 0 if the function e is not total. The second part is easy, right? If e is not total, then there exists an input where phi of e does not converge. Therefore, there exists an input that no matter how big f of s is, this does not converge. Therefore, you always output 0 as long as your s is big enough to include this input. Right? You might finitely many times give an output 1, because you're only looking at input values where it does converge, but there is an input where it diverges, then the first case never applies for that input, therefore you always get 0. So now suppose that e does correspond to a total function. If e does correspond to a total function, we have to see that from some point on g e of s is equal to 1. Why is that true?
Could you define a total computable function, which is just the maximum of the amount of time it would take for your function to converge on all the previous outputs?
Exactly. We had this function t over there. Now this function t we can't do because we don't have a function g, but we can try to do something similar. If we look at the function t of e, which is the least t greater than t of e s greater than s, such that phi e t of s converges. Right? So here, what we're doing is just blindly looking for this time when it converges. Now, if it doesn't converge, it's a partial function. But if phi of e is total, then this search works for all functions. Therefore, this is a total function. Therefore, f, which is dominant, dominates it. Therefore, from some point on, f of s is greater than this time which it takes for this thing to converge. Therefore, from that point on, for all input values, you get this.